Not so long ago, due to a series of unfortunate events, I found myself in another country, the Republic of Kazakhstan. All other things aside, the first thing that caught my eye here was the active usage of QR codes. You can pay with your smartphone anywhere. Shops, restaurants and public transport have little stickers or specialized terminals for payment. Even official documents have a QR code for quick scanning of your information when dealing with government agencies. This is a very weird experience for me. The thing is, QR codes are not really present in my home country. More than that, they are feared. Let me give you some perspective. Just a couple of years ago I made a video for my Russian YouTube channel explaining the basic principles of QR codes. This was a very simple video for a kids math olympiad. It was quietly laying on the bottom of the internet until the COVID happened. As a measure of preventing the spread of the disease, the government started issuing QR code certifications for vaccinated people. If you are vaccinated, you could use your personal QR code to enter restaurants and use public transport. The views on my video skyrocketed and the comment section blew up. I was surprised by how many people were interested in what this QR thing is. I was happy right until I went into the comment section and saw all kinds of conspiracy theories and assumptions. Let's just say that not many people wanted to be vaccinated, and the new computer thing scared them even more. Some of the comments accused the government of fascist practices. In retrospect, they were kind of right. I couldn't find anything about assigning numbers, but I have found a very interesting part about plotting and waging an aggressive war. The other comments looked outright insane. But what surprised me the most in this strange mix of anti-Semitic remarks and accusation of fascist practices, they repeated the same lines over and over again. Something about products, the price tags, the marks and the number of the beast. After some research, the main source of all theories could be traced. Within the 13th chapter of the Book of Revelation, someone found a connection between the QR code and the apocalyptic scenario. The chapter says that some beast ordered all people to make images of the beast, and anyone who would not worship this image and didn't receive his mark should be killed, and that no one might buy or sell if he doesn't have the mark, the name of the beast, or the number of his name, the number being 666. Despite the fact that everyone has a social security number, the idea of getting a QR vaccine certificate was really opposed. At first I was ready to go all out in the comments, because someone on the internet was wrong. But then I realized something. The last video I made about QR codes, it was kid stuff, really. And if I want to explain something more advanced, I need to step up my game. Perhaps my understanding of religious texts is lacking, but I do have a very particular set of skills that I've acquired over a very long career. And if there's any divine revelation hidden here, I will find it, and I will expose it. The PDF of Genesis for QR codes is ISO 1804 standard, and this 126-page manuscript describes its creation. In the beginning, I'm creating the grid. Now the grid is empty, darkness all over the surface. Let there be light! I see that light is good, and I separated the light from the darkness. I am creating the first version of the QR code. It's the simplest one, and its matrix consists of 21 by 21 modules. The other versions are bigger, so it's harder to show them on the small screen. There is also a micro QR version, which is really cool, but almost none of the QR code scanner apps could read them. Now, the square doesn't have any properties that would help distinguish the top from the bottom and determine that it is a QR code that we see and not a grid paper. So let there be finder patterns in 3 corners. That way we can always orient the QR code in the right way, no matter what angle it was shot from. The finder patterns always occupy 8 by 8 modules in these corners. The next problem is that there are no grids on real QR codes. For example, without the grid we would have no idea on which row and in which column this module is located. Therefore, to help the scanner distinguish the columns and the rows from each other, we need so-called timing patterns. These consist of lines of alternating dark and light modules that connect the finder patterns, plus one dark module situated close to the bottom left finder pattern, and they help to distinguish between rows and columns. Finally, strips of modules with thickness of 1 are reserved by now for additional information. All these elements from search patterns to timing patterns can be found in any QR code. A message is written into the rest of the modules by painting some of them black. But why use black cells instead of letters? Is that the Baphomet alphabet? Well, to hunt a demon we have to think like one. To do that we have to learn his language and understand how he encodes his messages. According to the manuscript, there are actually 4 main alphabets of modes of encoding that can be used: Numeric, Alphanumeric, Byte, and Kanji. So before writing our message, we need to specify the method of encoding that we use. For this, the first 4 modules in the bottom right corner of the QR code are assigned. By choosing one of the modes, we are painting the corresponding module black. Let's start with the byte mode to understand the basics. This alphabet contains 256 different symbols from a specified character set. Small and capital, letters, numbers, punctuation marks, and anything else you might need to write a message. Let's see how we can represent some information using it. For example, the 10-letter string Hello World. The next 8 modules in the QR code are allocated to represent the length of our message. Each module is assigned a number equal to a power of 2 in a specific order. The next step is to paint the corresponding modules so the sum is equal to the length of the message. In our case it's 8 and a 2. Now we are ready to encode characters themselves. How we can use modules to do that? If we use only one module, there is only 2 combinations of this module, white and black, and they can represent numbers 0 and 1 or letters A and B. 2 modules give us 4 possible combinations that could represent numbers from 0 to 3 or letters A, B, C and D. 3 modules gives us 8 possible combinations. And 4 modules give us 16 combinations that can represent numbers from 0 to 15 or letters from A to P. As you can see, by increasing the number of modules, we increase the number of possible characters that can be encoded. Moreover, if the number of modules that is used to encode one character equals n, the number of possible characters equals 2 in the power of n. To simplify the process of creating a block that corresponds to some number, we assign each module in a block a number that is equal to a power of 2. The sum of the numbers in the modules that are painted black equal to the number that block represents. In byte mode we have 256 possible characters that we can use in our message. So to be able to represent any character from this sheet we need 8 modules in a block. For example, the block on which the numbers 64 and 1 are painted in black corresponds to the 65th character, A. And a completely black block corresponds to the last character on this sheet, some strange French umlaut. That's why for every character in our message we are allocating a block of 8 modules in this specific order. Let's change each character to its according number on the character sheet. Each module of the block is assigned a number equal to the power of 2 in the specific zigzag order. The next step is to paint corresponding modules so the sum is equal to the number that represents a character. For example, the first character H is the 72nd character in this list, and it's equal to 64 plus 8. So we paint modules 64 and 8 in the first block. The other blocks are painted the same way. Finally, we indicate the end of the message by using a terminator. Oh, it's just 4 consecutive white models. Okay, so far there was no sign of Mr. Beast presence. Maybe it's because we encoded the message in byte mode. Why do we even need the other ones? The byte mode gives us every character that we can possibly need, even some really strange ones. You see, this way of encoding a message limits the maximum number of characters of our message to only 17 characters. And we can't use the last models because we'll need them later for error correction. But the numeric and alphanumeric modes use really smart ways of encoding that allow us to write more characters into the same code without increasing its size. Let's see how it's done. Numeric mode allows us to encode only digits from 0 to 9. It can be used for prices, telephone numbers, indexing books or inventory control. Following previous logic, to encode a total of 10 possible symbols, we need at least 4 modules. 3 modules are not enough. They make it possible to encode only 8 numbers. If you break the same modules into blocks of 4 squares, 34 digits fit. This is more than if you use 256 character alphabet. So, the fewer characters in our alphabet, the larger the message fits into the QR code. But this approach is not very effective. By choosing to use only 10 out of all 16 combinations, we actually use only 62% of the available space. How can we fix it? Well, in the numeric mode we actually allocate not 4 but 10 modules for encoding. It gives us 1024 possible characters to encode. Let's say I need to encode a date. Before encoding, I split it into the groups of 3 digits and encode each one of them as a 10-bit number. There are only 1000 possible numbers from 0 to 999, which gives us almost 98% utilization. In a sense, we represent our message as a word written in a language whose alphabet contains 1000 characters. This encoding method, where we pack 3 digits each into the block of 10 modules, allows us to create a message 41 characters long, given that the message consists only of digits, of course. As you can see, this encoding method tries to squeeze as much as possible out of every module. A similar method is used when we are encoding in alphanumerical mode. The alphanumerical mode allows us to encode the above digits, A to Z upper characters, and some symbols, which make it the best option for encoding the links to websites. There are 45 possible symbols in this alphabet, and by encoding them one by one, it will require at least 6 modules and give us only 70% utilization. Not good. To increase it, we use the same approach that we did in the numerical mode. So, we split the strings into pairs of characters and encode them instead. In a sense, we make every combination of symbols into a new character. How many possible combinations are that? If I write out in a row all the combinations with the first symbol, then the second, and so on, I get a rectangle of 45 by 45 pairs. This means there is only 45 in a power of 2 possible pairs, so we need at least 2025 combination of modules. This can be achieved with only 11 modules, which give us almost 99% utilization. And the last one is kanji mode. There are 6090 characters in this alphabet. To accommodate this, 13 modules are used for each character. It gives only 70% utilization, but no tricks are used here. Because of this, only 10 such characters fit in our size of QR code. Another thing that I've noticed during my time in a country is that the codes are readable from any phone, and no matter what condition they are in. Don't paint it over in any light, even with the logo covering half the code. Just point your potato camera and the code will be read. Well, all of that is achieved through error correction. Let's get to the byte mode, because it's much easier to show visually. There are 4 levels of error correction, and depending on the level we have to allocate different space in the QR code for error correction modules. The higher the level of error correction is, the more error correction blocks we need, and the less space is available for our message, but the more damage code can handle. For this version of QR we can encode from 7 characters on high level up to 17 characters on low level. Also, we must indicate the level of error correction. As you can see, we have only 4 levels, so we need only 2 modules to represent them. I choose low level of error correction. How do I indicate it on the code itself? For that we have space that we have left for additional information. So I paint the first 2 modules to the corresponding level of error correction blocks. Let's get back to our original message, hello world. The low level of error correction gives us a maximum message length of 17 characters. The remaining 7 blocks are used for error correction. But our message is only 10 characters long, so now we need to fill this unused space. For that, 2 alternating characters are used from the character sheet, characters numbers 236 and 17. Why them? It's not explicitly stated in our PDF of Genesis, but probably because they create a contrasting pattern and are unlikely to be confused with meaningful data. For these part characters we are allocating 7 blocks of 8 modules, the same way we did it for the characters in our message. The timing pattern that stands in the way is ignored and we jump over it. After that, each module of the block is assigned a number equal to a power of 2, and then corresponding modules are painted, so the sum is equal to the number that block represents. So, with the message modules that we already encoded, we only need to fill the error correction blocks. By this point, I thought I was ready to meet any Kabbalistic beings, but I definitely was unprepared for systematic Reed-Solomon error correction in Galois fields. Math so complicated that it crushed me like quantum physics in my 3rd year at university. You see, the PDF of Genesis that was my guiding light so far has left me with a mere short paragraph that could be written in kanji as well. Okay, maybe error correction blocks are not so necessary because our message is already there? I tried a bunch of QR reader apps, but none of them could decode it at this stage. You can try it yourself, it just doesn't work. It was like my hope of encrypting the code by hand was slipping away. In the midway of our mortal life, I found myself in gloomy wood astray. I looked aloft and saw the planet's beam that leads all wanderers safe through every way. By examining the sources, I found a couple of leads that might help. According to the 17th chapter in the Gospel of Mark, the name of Christ will cast out all demons, and the 10th chapter in the Gospel of Luke says that even the devils are subjects unto us through God's name. No wonder the past so far was bumpy, there is always hell in every hollow world. So from now on, I will perform a little exorcism and show you how you can create error correction words for the name of God. Using a character sheet, I assign a number to each character according to the byte mode alphabet. For these numbers we need to create so-called code words, error correction numbers that will help us to restore the original numbers if some of them were corrupted. The Reed-Solomon error correction works in such a way that we can only recover half the number of code words. In this example, if I want to recover one corrupted symbol, I need to find 2 code words. First thing that we need for that is the generator polynomial. We create a polynomial in such a way that we know its roots, and the number of its roots should be equal to the number of code words. So in this example we need 2 roots, let them be 1 and 2. This means that when x is equal to 1 or 2, the generator polynomial is equal to 0. Now we need to create the polynomial from our message. First, coefficients of this polynomial are equal to the numbers of our original message, and this polynomial is multiplied by x in the power of 2, the number of code words. To create the code words, all we need is to perform polynomial division between our message polynomial and generator polynomial. The result of the division is the quotient q of x and the remainder r of x. You can pause the video and try to find them yourself right now if you remember the school math curriculum. The difference between the message polynomial and the remainder polynomial is equal to the quotient multiplied by the generator polynomial. Because of the fact that this difference has a generator polynomial as a factor, it is equal to 0 when x is 1 or 2. This property allows us to use the remainder as code words. After division we get the following polynomials. In our case, the remainder polynomial is 1822x minus 1604. After subtracting the remainder polynomial from the message polynomial, we get a complete message to be transmitted. And the factors of the last two terms are our code words. If you didn't understand this part, in the description you can find links to in-depth articles and videos on this topic. These code words are really magical, and now I will show you how we can recover a corrupted message using them. Upon receiving the message, we substitute x in the equation using 1 and 2, and if it equals 0, we know the message has not been corrupted. But let's say some demon changed the first number to 77 to change the first message to mode. Not only can we see that the message was corrupted, but we can use the code words to correct one error and restore the original message. All we need is to assume that some coefficient is wrong and replace it with a variable p. We know that this function should be equal to 0 when the x is equal to 1 or 2, so we substitute it. Solving this equation gives us the original coefficient in both cases, 71. So the first letter is restored. If they are different, we try the next coefficient until we find the corrupt one. Sadly, we cannot use this exact approach for QR codes. With our 8 modules in each block, the maximum number that could be encoded in this block is 256, when all the modules are painted black. But our code words are in the thousands and one of them is negative. That's where Galois fields come into play. The main idea is that we don't use regular arithmetic, which allows us to work with numbers only up to 255. In this field, addition and subtraction are performed using XOR, exclusive OR, while multiplication and division are based on logarithmic and exponential tables. Despite the different arithmetic rules, the general principle of code word generation, error detection, and correction remains the same. With this approach, all of the numbers stay in the range from 0 to 255, which allows us to encode results into 8-bit blocks. But doing it by hand, even for a 3-letter word and 2 code words, are really hard task. The original message "Hello World" has 10 letters and needs 7 code words, so doing them by hand is out of the question. The main problem is that we as humans are not really prepared to perform multiplication in such different way. If you want to challenge yourself, you can find a link to the article that explains new rules of arithmetic in the Galois fields and a 16-step solution for a simple message. But do you know who is really good at this new arithmetic? Computers. I initially considered using Python to tackle this challenge, but the Book of Revelation and the Bible has something to say about devious nature of snakes. So, to avoid any serpentine connotations, I decided to opt for a Godot game engine. It seemed like a fitting choice given its divine-sounding name. This program for step-by-step QR codes generation is available on my website as an open source tool, and you can use it. Additionally, the animations featured in this video can be found on my website as well, and are free to use for educational purposes such as lectures or demonstrations. If you find these resources useful and would like to support my work, consider becoming a patron. By supporting me, you'll gain access to high-quality versions of the animations, dark and light versions of materials for presentations and printing, exclusive and behind-the-scenes content, early access to new resources, and convenience of easy downloading. Using my program, I successfully calculated the 7 error correction blocks needed for the original message "Hello World". Then I assigned a number equal to a power of 2 in a specific zigzag order for each block, and then painted the corresponding models so the sum of the painted models were equal to the error correction number. Is it ready? We still have a big problem on our hands. Large columns, rows and clusters of white and black models make individual cells hard to distinguish. Well, maybe not in this case, but let me take the issue to the absurd level. I make a message that consists of the last 17 characters of the byte mode alphabet. Remember this strange French umlaut? If I try to encode them like we did before, we will get a very disturbing image. When we have a large area with no models painted, or a large area fully painted black, it is very difficult to scan the QR code properly and distinguish different models. That's where masks come into play. Now stop, I can hear you say, masks? We just got rid of them. If you want to suffocate me with your liberal cloth and forbid the air of freedom, you'll have to take it from my cold dead lungs. I meant different masks. QR codes use one of the 8 masks to make the image less uniform. The chosen mask is XORed with the data and error correction blocks to avoid problematic patterns. Visually, it works like this. First, we are overlapping QR code with the chosen mask. Then all bright and dark models are painted white. And all gray models are painted black. This operation is performed only on data and error correction blocks. Mask is not changing finder pattern, timing patterns and additional information. When we are decoding, we just need to perform the same operation and the QR code will return to its previous state. Using my program you can choose any of these 8 masks, and in most cases it will work just fine. But the real algorithms calculate all the masks at the same time and arrange a beauty contest between them to choose the most attractive mask for the scanner. The best mask is chosen based on which one has the least penalty score. Penalty scores are determined by 4 rules. First is prevention of long vertical or horizontal sequences of models of the same color. Second one is minimizing large areas of the same color. The third one is avoiding patterns resembling the finder pattern. And the fourth is achieving an overall balance between dark and light models. Then the mask with the best score is applied. Let's go back to our original message, "Hello World". And since my program allows you to choose any mask, I will take mask number 3. Now it is necessary to specify in the QR code itself which mask was selected, to let the scanner know what mask to apply during the decoding process. For this we allocate the next 3 models of the additional information, because 3 models allow us to encode up to 8 numbers, the number of available masks. Each module is assigned a number equal to a power of 2. And then we paint the corresponding models so the sum equals to the number of the mask. In our case, these are models with the number 1 and 2, because we have chosen mask number 3. Alright, we successfully dealt with our data and chosen our mask. Now we come to an essential step, the creation of error correction code words for our additional information. We have already seen how vital these error correction modules are for recovering our data if part of the QR code gets damaged or obscured. Just like the data, additional information is also susceptible to damage. That's why we allocate 10 next modules for error correction, which allows us to correct 5 corrupt modules. Then we follow a similar procedure as we did for the data. We calculate the 10 error correction blocks using the BCH code and map them into corresponding QR modules. Again, this is quite hard to do by hand, so I suggest using my program, or if you want to do it yourself, I've left a link in the description to an article describing the process. In the next step, we apply this mask for 15 bits of additional information, the same way as we did it for the data. The only difference is this mask is always the same. At this step, a QR code can be read. But just to be extra safe, I want to prevent a case in which the top left corner is lost. So I will copy additional information in the 2 remaining corners. Our code is ready. In theory, one could read a QR code without having the additional information intact. Each QR code could be generated using one of 4 levels of error correction and one of 8 masks. So we can just try every possible combination of EC level and masks. 4 times 8 equals 32 different combinations to try. But it would take a human to read through all of the results and pick out the one that makes sense. And in cases where the original message isn't a standard text message but some form of coded data, it could be nearly impossible to identify the correct result. That's why we take all the necessary steps to protect and preserve this additional information in our QR codes. Okay, look at this, everything can be explained by math. Again, I know, right? But I didn't manually encrypt the code. And what about the Galois fields? Anyone can say that they skipped a bunch of steps and just programmed it. Deus ex machina. Besides, there is something magical and shadowy about this whole thing. Take for instance the error correction code words. They like incantations, easy enough to cast but very difficult to explain why they work or how to create one. But just because we can't explain something doesn't make it devilish. It may be divine in nature. Take crops for example. Even a child can explain that if you plant a seed into the ground and water it, it will grow. But it's incredibly difficult to explain the mechanism of this process. And there is nothing diabolical about it. When I was studying QR codes, all I saw was love and care for the safety of our data at every step of the way. Love and care that no demon is capable of. And if you're still not convinced, much like how religious traditions have found ways to adapt to the modern world, like creating solutions for using electricity on the Sabbath, we can find a solution for this QR quandary too. Given the level of error correction embedded in the QR codes, there is nothing stopping us from developing a new standard that encodes or straight up places the name of God into every QR code. We could call it Ortho QR or Halal QR or Kosher QR. This would symbolically ensure that every transaction involving these codes is protected and sanctified. Yes, they will perform a little bit worse and read less often, but I think that's nothing compared to eternal damnation. In the end, I wanted to go back to the comments under the old video and continue the argument, but theological debates can go on indefinitely. After all, within the text of the Bible, there are quotes for all situations applicable to life, even one that hints that you can find any interpretation you want.